Hi, today I'm talking about LeetCode problem 983, minimum cost for tickets. This problem asks you to write a function that will take a list of days and a list of costs. And so days works by having a number of days that you're going to want to have a train ticket for. So in this example, you want to have a train ticket that covers day 1, 4, 6, 7, 8, and 20. And costs is always a 3-element array, with the 0th element being the cost for a 1-day ticket, so a ticket that's good for just 1 day. The first element is a ticket that's good for 7 days, and the third element is a ticket that's good for 15. So the problem is asking you to write a function that will take days and costs and return the minimum amount you would have to spend to cover days with tickets that you purchase through costs. So in other words, we want to cover, like here I have this example written out, we want to cover days 1, 2, 9, 35, 51. So we could cover them all with 1-day tickets. That would cost 2 plus 2 plus 2 plus 2 plus 2. But possibly there's a cheaper way to cover all of these days using tickets that cover more than 1 day at a time. So what we want to do is figure out, what's the cheapest cost. And so when I was thinking about this problem, how I thought about it first is I wanted to approach it recursively. So when I think about recursion, I think about what's the base case, and I think about what's the recursive case. So the base is just something where we know the answer. And the base case would be if there were no elements in my days list, like I'm looking for 0 days, then it costs nothing. It's free. If I'm looking for just 1 day, then what it costs is the minimum of my costs list. So if for whatever reason it was cheaper to buy a 7-day ticket or a 30-day ticket than it was to buy a 1-day ticket, then sure, I just need to cover my 1 day with the cheapest possible ticket. And then if I have anything more than 1 day costs, that will be my recursive case. And I guess I'll just cover that slightly. I just saw I titled this section base. So the recursive case, here what we're asking is how can we break this problem up into subproblems? So the subproblems get closer and closer to our base case. And how I've illustrated that is I've just shown that, okay, we can think about the cheapest way to cover this whole list of days is going to be the cheapest way to cover the first section of days plus the remaining section. So when I say the first section, that's variable. It could be 1 day, could be 7 days, which would cover 1 and 2, could be 30 days, which would cover up to 9. So what's the cheapest way I can cover that section plus the cheapest way I can cover all of the remaining sections? And so if I think about it like that, then I can just divide this up to be recursive. So let's take a look at implementing that. What I did is here's the function that LeetCode requires me to write, and I'm just going to call into my helper function, cheapest cost. I'm going to start it off with a 0 for the starting index, and I'm going to supply, actually this is slightly more complicated than it needs to be. Let me go to my first successful submission. And that will be a bit more clear. I wrote it a bit differently just to be more performant. So, okay, I'm going to call my cheapest cost function, which takes a tuple of my days and my costs. And the reason for converting the days and costs lists into tuples is because tuples are immutable, and therefore they can be used as the key in a dictionary because they're immutable, whereas a mutable list cannot be used as the key in a dictionary. And I will want to use these items as keys in a dictionary for when I do memoization to speed up the recursive case. Okay, so here's my cheapest cost function up here on line 9. And what it says is I'm going to compose this, this tuple of my days and costs list. If this is already in my sols solutions dictionary, then just return the value that corresponds to this key. So this is what I was talking about with memoization. Because the recursive case, or because recursion may require me to recompute things that I've already computed. So when I compute this list of 1, when I next compute this sublist and this subsection and this subsection, I'm going to be recursively making calls that I've already calculated, which is the point of checking to see, wait, have I already considered this pair of days and costs in my solutions dictionary? And as I'm looking at it right now, I realize I don't need to add costs. Costs are always the same. I'll talk more about that in a minute. But anyway, that's the purpose of this memoization. What it does is it speeds up the recursion by obviating the need to recalculate things that I've already calculated. Okay, this is the base case I mentioned before. I have less than 1 day, so then I can just return 0. I suppose there's another base case for if I just have exactly 1 day, although it can be handled by the recursive case as well. So there's no need to special case that, actually. And so here I am with the recursive case. I just store the minimum of, and then this is just going to be a sequence of three options. So the minimum of cover the first day, cover 1 day from my days list, cover 7 days from my days list, or cover 30 days from my days list. So it's going to be the minimum of calling the cheapest cost with the first argument, the days list, being the result of calling my cover function with cover 1, cover 7, cover 30. And to just show the cover function, it's up here on line 5. It's just going to say, okay, starting from the first day in the list, return a tuple of this generator expression, which just says all the days that have a difference from the start day of more than 7. So basically we're just cutting out, of more than n, not more than 7. So n is one of the arguments supplied. So if I supply this with 1, it's going to cut out all the days that have a difference of less than 1 with the start day. So basically it would cut out the start day for 1. If I sent in 7 into my cover function, then it would cut out all the days that have a difference of less than 7 from the start day. So this is not the most efficient solution. And actually when I ran this, it ran in something like, well, I guess 44% for speed. I thought it ran slower than that, but I guess it did not. But 44% for speed is not the best we can do. The best I got it up to was here, where it was something like 87% for speed. And so the way I got it to go even faster is largely by improving the memoization part. And by changing the cover function. So when I say improving memoization, you may recall in my previous example, let me show you my slowest solution. In the slowest solution, the key in my memoization dictionary was a tuple of the days and costs. So that requires me to construct a tuple of these 2 other tuples. And it requires every time I look up, like, is this key in my solutions dictionary? Every time I look that up, I've got to hash this key. And hashing the key could be relatively expensive, given that it's a tuple of tuples. And I don't know how long they are, for example. They could be any length. So this is a relatively small cost, but it is a cost. And so what I've done here when I've sped things up is I replaced my key. It's no longer a tuple of two tuples. It's just the starting index. So I just refactored this code a bit to use an index instead of modifying the days list. So instead of cutting out a day every time, or 7 days or 30 days, I just cut out an index to say, okay, start considering from the 0 position of the days array, the 7 position of the days array, whatever position I want to. So I don't actually have to cut up the days. I just have to adjust the starting index. So the key is simpler. So looking up in the solutions dictionary is faster. And then the big performance improvement from using start index is that my cover function no longer has to generate a new list. So I no longer have to make this check for every day in my days list. So this is kind of an O of N operation to call my cover function, or it was in the slow version. But here we can just reduce that to what we do is we just say, okay, our start is the starting index of my days array. My result is going to be the starting index as well, the length of my day list, while our result is less than the length of my days list. So while we go through the whole day list, and days sub result, so the day of my current result less the start value is less than n, the number of days I'm trying to cover, then I'm just going to increment result. So this is just going to push result up to be essentially the new starting index. And if that wasn't clear, maybe I can just illustrate that here. We can say our days are 0, 1, 5. And I guess we'll say 9 too, just so we have one decent example. Okay, so my starting index is going to be 0. I'll write that below. So SI is 0. Okay, so while days sub 0, and let's say we want to call cover for 7 days. So, okay, while my days sub starting index less the start value, which is 0, while that is less than the number I want to cover in, while that's less than 7, because we're calling cover of 7, then we're just going to increment result. We're going to increment I guess I should say result as 0, because result will have the value of starting index when we start out. Okay, result is 0. Good. So we increment result, and we're going to push it up to 1. Increment result to 1. Okay, 1 minus the starting value is still less than 7. So 1 minus the starting value is 1. That's still less than 7. Okay, we're going to increment result again. So that's up to 2. Send that up here. Okay, result, days sub result less days sub start. That's still less than 7, so we're going to increment it again. Okay, days sub result less starting value is now 9. That's not less than 7. Okay, so we're going to return 3 as my new starting index. I realize that's a messy drawing, but hopefully you can just see the logic that I'm trying to illustrate there. And so that's a bit more complicated to talk about and maybe to reason about, but it has the benefit of being substantially faster. So this was 40 milliseconds for the slightly more complicated version compared to what was it, 136 milliseconds. So, we're substantially dividing the speed. And then I realized I'm going a bit long, but I also wanted to just start talking about things I learned while working on this problem. So one thing I learned was, read more carefully. And this is probably something that can apply generally, not just to this problem. So I expect if I continue to list my lessons for problems, that I may see some repeats. But the problem for me was that when I read this, I was a bit careless and thought that it just, I don't know why I thought this, but I thought that days was limited to be the days of a month. So they have an example here with 31 days. So my first attempt at a solution, you can see I actually hit the time limit exceeded. And that surprised me because I thought I had tested it with the max input value. I thought I had tested it with 31 days and my code worked. So I thought like, oh, cool, that's fast enough. But actually, they say very clearly that the constraint is days should go between 1 and 365. So I hadn't tested the max case. I just tested like a very small version of it. And that's why I tried to submit code that was way too slow. And I think what I submitted there was just this solution, but without the memoization at all. So I thought like, oh, I don't even need to do memoization. That's cool. But then I immediately failed. So that wasn't good. That leads to the second lesson, which is test the worst case. So if you're explicitly trying to test the worst case, and for me, that would have solved my problem. I wouldn't have submitted bad code once. So I would have said, okay, what is the worst case? I would have checked. It would have said 365. And then I would have failed my test case as opposed to failing the submission. And then the third thing is the key in memoization. So I talked about this before. I was pretty careless about what I was going to use as the key for my memoization. So yeah, in my early submissions, I just have costs in there for absolutely no reason. In my early solution, I was shortening days, but I didn't even need costs at all. Because it's constant. And in fact, I don't even need days to be the key. I can just use the starting index. That's a simpler key. And it means that the code will be written such that I don't have to change the list. So with a bit more thought, I could have just written the faster version of the code the first time. And that would have been better. Okay, that's it for me. If you enjoyed this, let me know by clicking the like button. If you want to see more content in a similar style, you can subscribe. If there's something you want to see in particular, please leave a comment just to let me know you're watching. Thank you. Bye-bye.